Hey, this is my solution for the problem that we did on Friday of week 5. And the question was about a capacitor and a resistor hooked up together in series. And so we wanted to think about first if we try to connect the voltage source to this network, what would happen? And so we can use all of our tools to think about this idea. So we have that the voltage across a capacitor is Q over C, and the voltage change across the resistor is I times R. And so the idea is that at time equals 0, the voltage drop across the capacitor is 0 because there's no charge. But that means then, therefore, because the voltage drop across the capacitor is 0, the voltage drop across the resistor has to be the voltage of the battery. So that means that the voltage drop across the battery, the voltage provided by the battery, is equal to I times R. So that's at time equals 0. As time goes on, that means that the charge is on the capacitor is getting bigger. So the change in the voltage across the capacitor is now greater than 0. So that means that the potential across the resistor has to now be less than the voltage of the battery. Why? We know that the change in the voltage across the resistor, and that you lose voltage there, and the change of the voltage across the capacitor has to be equal to the voltage of the battery. Okay, so that's actually enough information, but just to check, let's look at for time goes to a very, very long time. And eventually, the biggest that the voltage drop across the capacitor can be is equal to the voltage of the battery. That's the biggest it can be, really. So that means that once that happens, it's not getting the voltage drop isn't getting any bigger, but it also means that the charge has reached its maximum for that battery. And the capacitor, of course. So since the charge isn't flowing anymore, the current across the resistor there, therefore, is 0. There's no current through the resistor, so the voltage across the resistor is 0. So one of the things I want you to notice about this is all these symbols I'm writing down, it's really just mathematical shorthand. None of this is really equations for you to memorize. You want to sort of reason this through. But what we have here is enough information. So if the question is, what does the current do? That means that the current, it ends at 0. Where does it start? Well, it starts here, that the current is the voltage of the battery divided by the resistance. So it starts at that value and then goes to 0. And so if I graph that, it looks like this. Now, simply telling you that it starts high and ends low isn't really enough information to tell you the shape of the curve. But what we showed in class is that the current starts high and goes low with an exponential decay. And so this curve is the initial value times e to the minus t over RC, where this value RC is called the time constant. Okay, so we start here at I naught, V of the battery, divided by R. So now consider this. So if we discharge the battery, therefore we have a capacitor a resistor, and now we're just going to have a fully charged, meaning that the potential drop across the capacitor is equal to the battery. In other words, it's at maximum. And then we connect to the resistor. Okay, so now what's going on? Well, now we start off with the voltage drop. So again, T equals 0 when we do that. That means that the voltage drop across the capacitor is at its maximum. So the voltage drop across the resistor is equal to 0. So that, wait a minute. Oh, wait a minute. No, that's not right. See, that can't be right. Two things I know. So if I have a battery, so what a battery does, so this is realizing my mistake. A battery enforces a total potential difference that's not 0. But once we hook these two things up, in fact, because they're in series, they have to have equal and opposite potential differences. So one way maybe to see that is to do a quick Kirchhoff law, and whatever we lose through a resistor, so through the capacitor, let's say first, has to be offset by the change of the voltage across the resistor. So I was wrong about that. The voltage difference across the resistor has to be equal to the battery. And I'm not worrying too much about the signs here. I'm just going to figure out what the current looks like, because I'm just showing the magnitude of the current. Anyway, okay, so what that means is that this is IR. And so the current starts at the voltage of the battery divided by the resistance. In fact, this is exactly the same as it was before. So we'll just check now as time goes on. Then eventually all of the charge, the net charge on the capacitor plates has left. And so now there'll be no current at all, and it will have dissipated the energy that was inherent in the potential difference with the charge on the plates. So by charging up a capacitor, you've stored energy, and that energy is going to be dissipated. By the resistor. And so I'll make it a little bit smaller here because it's exactly the same, but over time we start with some initial value that's again the battery over R, and it drops off exponentially. Okay.